Okay. All right. So I'm going to be doing a Lab 2 video, just kind of an introduction, kind of what's going on. And then make sure you download the new write-up and the new PowerPoint. Because the old PowerPoint, the graduated cylinders, you could barely read where the line was. So what I did is I went in and increased the contrast and made it better. It's not, I don't know why they didn't use glass, they used plastic, which is like, the reason why they have plastic is because they don't break, which is great for student drawers. But when you're doing a demo, anyway, should have used glass. So, and then the write-up I changed considerably. I've made it, in my opinion, clearer. And I also extended the date because I messed up when I was doing the calendar. I put Lab 3 as Lab 2 and vice versa. So I just moved everything out to give everyone extra time to do them, to make sure there was no issues with the mix-up. Because a lot of people were doing Lab 3 thinking it was Lab 2 because that's how I labeled it on the calendar, but the lab itself was labeled 3, so there's some inconsistency. Anyway, I fixed all that. So, all right. So any questions about where we are, where we're going, etc.? Okay. You're going to have your quiz 4 available on Wednesday. It will not be a proctorio. In fact, the rest of the semester, we're not doing that. And then I'm debating on lab or on exam 4, whether it to be a take home. I'm leaning more towards it being a take home than a multiple choice. Multiple choice is nice because it's automatically graded, and you get your grades really fast. I'm debating. It's not 100%, but I'm leaning that way. Exam 5 will be definitely take home. And lab, your final, I'm believing, will be a hybrid, part take home, part multiple choice. That's where I am right now. Now, tomorrow that may change, but as of now, that's where I am. Okay, so again, anything else? All right, so let's jump in. Now, today is going to be kind of an interesting day. We're getting into chemical reactions, chapter 7 today. And what I'm going to cover today is what is a reaction and then how to balance it. Now, we've talked about chemical reactions in the past. And we are going to do something today called balancing them. And so let's start off here. Okay. The world we live in has got chemical reactions going on everywhere, ubiquitously. You cannot look anywhere and not find a chemical reaction going on. There's a book, an old textbook I used to use. It's called, what's the title? Something like Chemistry is Everywhere, or Chemistry is in Every, something like that. And I truly believe that that's the case. It's just, yeah. And then, so what is a chemical reaction? That's the big deal. And a chemical reaction is something where nature changes things around to become more stable. Excuse me. So the driving force in this whole thing is stability, like I've been talking about for the whole semester. And I'll continue to talk about this for the rest of the semester. When you get into your next chemistry class, assuming you do, whether it's biochemistry, organic chemistry, or general chemistry, which is inorganic chemistry, stability is the name of the game. Reactions occur only because they're more stable. And there are two factors that determine that. That's randomness and potential energy. And we've talked a lot about potential energy, not a lot about randomness, but that comes into the picture as well. Okay, so when a reaction happens, that means we start with, let me go over here. So when a reaction happens, we've got two parts to the reaction. Okay, we have something called reactants, is what you start with. And that's always placed on the left side. Just standard procedure. Reactants are always on the left. What happens to the reactants is always on the right, and those are called products. Now, if we're talking about biochemistry, it's not called reactants, it's called substrates. And I'll just mention that as a parenthetical comment. So whenever you're, if you're not going on to Chem 400, but you're looking at some other kind of general biological things, you may see the word substrate. And that's the same thing as a reactant. So you have substrates, products. Okay, and then it's left and right. Okay, so how do you know a reaction is happening? Typically, there is something physically that goes on. And 99% of the time, there's physical evidence. Okay, in other words, there's a color change, some solid forms, or solid goes away, or gas is produced, something gets cold or hot, or you know, light's given off in the form of energy. Those are all indicators that something's going on. And it's important to understand that if nothing happens when you put two things together, things still may be happening. Still may be happening. It's just that your observation of them is not allowing you to perceive that something is going on. Okay, so this list needs a number 6 here. This is a non-observable physical or chemical change. Okay, so in other words, we take water and we take, well, as an example, last Saturday night, we had a Halloween party, and I was there, and I came as a wizard, and I did 2 magic tricks for everyone. One was I took money and I soaked it in isopropyl alcohol, 50%, and I lit it on fire, and the money didn't burn. Okay, well, my point here is that when I put the isopropyl alcohol and water together, it still appeared like water. But things were going on there that were not observable with my naked eye. Now we could look at using an instrument or something else, but as far as, and what if I was blind, it would still be going on. Okay, so bottom line is we have color change, formation of a solid or disappearance of a solid, evolution of a gas. It either gets hot or cold. That's what they're talking about, absorption of heat. Things are getting cold because it's absorbing energy. So that's when energy is going away. We have less kinetic energy, which is called heat, or light energy is being given off. Okay, but just because we don't see it doesn't mean it's not happening. Okay. All right, so we have reactants, products. Okay, now when we have a chemical reaction, things happen. Chemical bonds need to be broken and reformed to product bonds. Also, importantly, no atoms are lost or gained, no exceptions. Now, when I say that, we have Einstein's famous E is equal to mc squared. if that mass disappears, it's converted to energy. So really, even though mass may appear to be gone, it's in the form of energy. Now, when you, or if you ever study nuclear chemistry in physics or in a chemistry class, you will work with this equation a lot. Because what happens is, for example, when we have a nuclear power plant, the reason why we have nuclear power plant and using uranium or plutonium in that power plant is because we lose mass, and that mass is converted to heat energy. And that heat energy is converted to steam, which turns a turbine, which turns a generator, which produces electricity. Same in a submarine or an aircraft carrier. Same thing, we produce energy, which turns a electric motor that turns the prop on that ship. So in nuclear chemistry, nuclear physics, we interchange mass and energy all the time. Okay, as far as our class is concerned, number 2 is what we're going on, okay? So no atoms are lost or gained. Okay, all right, so let's look at the situation. Okay, we have sodium metal. Now notice there's a little S there, and a little L, and a little G, and a little AQ. Okay, the S stands for solid, it's lowercase. The L was for liquid, lowercase. G is for gas, and AQ means it's an aqueous substance dissolved in water, means it's ionic. So whenever you see the AQ, we're going to be talking about that on Wednesday. Whenever you see the AQ, that means it's ionic. Okay, so that means NaOH, sodium hydroxide, is ionic, means it's really sodium ions and hydroxyl ions dissolved in water. And actually, the water molecules surround the sodium ion, and they surround the OH, the hydroxyl ion as well. That's what the AQ means. So as soon as you see AQ, think ionic. Wednesday, we're going to talk about that in a lot more depth. Okay. Now, they do not participate in determining whether this equation is either gained or lost atoms or balanced. Okay, the AQ just means what is the physical state of that particular element or compound. So the physical state for this sodium is it's solid. Water is liquid, doesn't have to be liquid, it could be solid water like ice. This is gaseous hydrogen. And then of course we have the AQ, which means it's ionic, dissolved in water. Okay, ionic means it's dissolved, ionic, and it's dissolved in water. Excuse me. Okay, I haven't coughed all day. Okay, all right, so let's look at, let's see here. Let's look at this reaction here. Okay, so because there is heat, we know a reaction occurred. And this is given off heat. But, a reaction can occur also if it gets cold or it absorbs heat. Okay, so we have sodium metal plus water, arrow to the right. Now, when we get into more advanced chemistry, you're not going to see an arrow, you're going to see it like this. Okay, but for our class, it's going to be an arrow to the right. And that gives us hydrogen gas and sodium hydroxide. Okay, now we need to write, whenever we write a chemical reaction, we have to make sure it's balanced. That's because we want to make sure that number 2 is applied. In other words, no atoms are lost or gained in the reaction. That means on the reactant side and the product side. Okay, so the first step is we're going to do actually, this is going to be, first thing we're going to do is we're going to do a reactant and a product inventory. Okay, so what atoms do we have in this equation? We have nitrogens, hydrogens, and oxygens. Excuse me. Now notice I write that underneath the arrow. That indicates that this nitrogens stay there. They do not go away. We're just looking at nitrogens on the reactant side, nitrogens on the product side, hydrogens on reactant side, hydrogens on the product side. Well, we're going to take an inventory, first thing. Now, when I say inventory, I'm looking at the numbers of atoms. Okay, so how many nitrogens do we have on the left? The way it's written.
1.
1. How many on the right?
2.
Yeah. So we immediately have a problem here. How many hydrogens on the left?
3.
And on the right?
2.
You can see we're already having problems here. Oxygens, it's 2 and 1. Okay, so we are going to modify the coefficients to achieve equation balancing. Whenever we change a coefficient, we need to do an inventory again. Subscripts will never be modified. The reason if we change a subscript, we're actually changing the physical molecule. We want to keep the molecules intact. Sometimes we need to work with fractions, and that's okay. There's a way of clearing fractions when we're all done. And if we have a element like nitrogen, which is a very simple molecule, we're going to leave that balance until last. And the GLS, AQ do not affect balancing. And sometimes the GLS, AQ will not be present. Sometimes it is, sometimes it isn't. Okay, so obviously we have a problem here. The ones in, nitrogen, hydrogen, and oxygen, none of them are equal on both sides. So we have to change it. Now, those are the coefficients. Okay, notice there are no coefficients out in front. That means they're all 1. So some of my students like to put 1s there just to be consistent, which is fine in my class, okay? 1s are really there, okay? Okay, so notice we had 1 times, oops. We had 1 times 1. Notice there's coefficient of 1 there. That's how we got the 1 nitrogen. 1 times 3 gives us 3 hydrogens. 1 times 2 gives us 2 oxygens. So the coefficient says 2 things. Let's see, where is a good place to put that? Okay. That says two things simultaneously. How many molecules we're talking about, and eventually we're going to talk about in Unit 5 how many moles there are. Okay, so molecules and moles you'll be using interchangeably here, particularly when we get to Unit 5. Okay, but for Unit 4, we're going to be looking at molecules mainly, and that's the purpose of that is for balancing. Mostly. Okay. So this means we have one molecule of NH3 and one molecule of O2, one molecule of nitrogen gas, and one molecule of water. But the problem is those coefficients net us an unbalanced equation. Because when we do the inventory, the nitrogens don't work out, hydrogens don't work out, and the oxygens don't work out. So now we're going to play a game. It's called Guess and Check. Guess and check. Okay, the guess part is we're going to change some coefficients to try to balance this equation out. Okay, well, let's change one of the coefficients and I'll show you what I'm talking about. Well, we have two nitrogens here, and we have only one over here. So if we were to change this to a 2, that would give us 2 nitrogens, which would balance our 2 nitrogens on the right. However, it would kick the hydrogens up to 6. And it wouldn't affect the oxygens at all. So we're not done yet. Let's go ahead and do some other changes. Okay. Well, let's look at the water now. Water over here on the right comes in, hydrogens come in 2s. So if we were to put a three there, that would give us 6 hydrogens and 3 oxygens. Okay, so the nitrogens are looking good, hydrogens are looking good, oxygens are looking poorly. So one way we can get, what do we multiply 2 by to get 3? Two times what is 3? Is it 2? Not 2. 2 times 2 is 4. It's not 1, because 1 times 2 is 2. What's in between 1 and 2?
1.5.
Yeah, 1.5. Or 3/2. 1.5 or 3/2. Okay. Now when we multiply 3 over 2 times 2, we end up with 3. So is the equation balanced now?
Yeah, it looks good.
It is balanced because what's on the left equals what's on the right. Unless that's so, it's not balanced. No exceptions. Unless we have a nuclear reaction, we have a big explosion where it's being all jump. As far as our class is concerned, left has to be equal to right. Okay. Now, it's balanced. The problem is, remember when I talked about coefficients over here? Coefficients are the number of molecules. Okay, so can we have a 3/2 molecule?
No.
Yeah, it doesn't make sense, does it? So what we can do is it's called clearing the fractions. Okay, so what is the denominator on 3 over 2? What's the lower number, the denominator on 3 over 2?
2.
2. So we're going to multiply everything by 2. Now I want you to think about, this is going to be like an algebra equation. What we do to the left, we got to do to the right. So multiply 2 times 2 is, this is a tough one now, 4. 3 over 2 times 2 is 3. 2 times 1 is 2. And 2 times 3 is 6. So that's how we're going to clear any fractions, as we multiply. And usually it's going to be 2 or 3. Rarely it's anything other than that. Most of the time it's 2. But we're going to clear the fractions. We multiply by the denominator of the fractions. And we're rarely going to have more than one fraction. Normally it's just one fraction. Okay, so we have 4, 12, and we have what? 6, and 4, 12, and 6. So fractions are fine when you're balancing. Just make sure you don't leave them that way. So this is balanced. How do you know it's balanced? If I ask you on a test, show me that this equation's balanced, this is what I want you to show me. The inventory of product and reactant elements. Now, this is probably the first equation you've balanced. And notice we didn't have an analytical method to do this. We just said, let's put a 2 here and see how it changes things. So we guessed at a coefficient and then we checked. Guess and check. When you get into Chem 400, guess what method you're going to be using? Guess and check. When you get up to physical chemistry, guess and check. Now, the cool thing about organic chemistry, organic chemists and biochemists never balance equations. So people that love balancing equations, there's a sad face when we get to those upper level classes. Okay, so let's do, are there any questions that, like, let me do a couple more and we'll see how things go, okay? All right, so any questions before I do, I'm going to do quite a few more here. Are there any questions about what we just did here? Okay, one question I always get from students is, where do I start? And my answer is always, it sort of doesn't matter where you start. Normally I go, leave these simple ones for last and go for the bigger, more complicated molecules. Because when you change the coefficient on a complicated molecule, you change more than one thing. Okay, so let's look at this guy here. Okay, so we have sodium, hydrogen, and oxygens. Okay. And this is okay, so we take sodium metal, throw it in some water, we get a whole bunch of gas produced, and we get a whole bunch of lye produced that's dissolved in water, and we get a lot of heat. A lot of heat. Okay, so is this balanced? Well, we don't know if it's balanced, so we do an inventory. Okay, so let's do an inventory. Remember, if there's nothing out front here, it is a 1. And when we balance equations, because heat is in the form of energy, not an element. So you're not balancing heat, only balancing physical elements. So the heat part doesn't come into balancing at all. It's there, part of the equation, but it's not part of the balancing aspect. Okay, so we have one sodium on the right. Good shape so far. We have two hydrogens on the left. We have two hydrogens on the right. Ooh, we're doing really well. Okay, we have one oxygen on the left, and we have one oxygen on the right. Okay. So did I do something wrong here? Notice on the right, hydrogens are two places. They're here and here. So really we have three. So keep that in mind when you're adding up the elements on both sides. Sometimes the atoms are in multiple molecules, but you still have to collectively put them all together. So on the right, we have a total of 3 hydrogens. On the left, we have a total of 2. So the hydrogens are the issue. Okay, so any suggestions where to start?
We could just start with a 2 like last time and see what happens.
To where?
The hydrogen.
Okay, so we're going to put on the right here or on the left? Which hydrogens are all over the place? I'm going to put the 2 here, the 2 here, or put the 2 there. Where am I putting 2s?
I'd put it at the NaOH.
Okay. All right, so now we have to do an inventory again. Okay. Notice that changed our sodiums. So how many sodiums do we have now? How many sodiums?
2
Two?
on the right.
Exactly, 2. Okay, how many oxygens?
2.
2. And how many hydrogens?
2 as well.
2 plus 2 is 4.
Oh, 4.
Okay. All right, so it's not balanced, right? Not balanced yet. Why? 2 reasons. 3 reasons. Oh,
Were we supposed to put the 2 in another spot? It looks like we just made it worse.
well, you can change a bunch of coefficients all at once. It's just anytime you change a coefficient, you've got to redo redo the inventory. For example, if you were talking about hydrogens, if we put a 2 there, oops. See, that would give us 4 hydrogens here. All right. But how many oxygens would that change? It's no longer 1, it's what?
2.
Yeah, 2. Okay. And we're still left with the sodium problem. You have 2 on the right, how many on the left?
2.
2, yeah. Okay, now it's balanced. Okay, sodiums, we have 2 here, 2 there. Hydrogens, we have 2 times 2 is 4. 2 here, 2 times 1 is 2, so we have 4 total. How many oxygen? We have 2 oxygens from the water, and we have 2 oxygens from the sodium hydroxide, so it's balanced. Guess and check. The check is the critical part, because you always have to do the inventory over again to make sure that it's balanced. Can't stress that enough. A lot of times students don't do inventory. They'll change something, they'll change one thing, but the problem is frequently it changes multiple things when you change a coefficient, not just one thing. And I want to stop for a second and I'll show you something. What I did, okay, I gave you, this is modules on Canvas. I've given you lots of practice on equations, and I also gave you an extra credit problem, which is particularly a pain to balance. That's why it's extra credit. Okay, so I gave you 5 worksheets besides the other work, the chapter 7 worksheets. Okay, gave you lots and lots and lots of practice, because some people will do this and they'll go, oh yeah, I got it, and other people will they'll go on and on and on, and and all of a sudden they'll go, oh, it'll just like a beam, and all of a sudden it's an aha moment and it clicks. And some of these equations are simple and some are complex. When you do a complex one and you get totally frustrated, skip it and come back to it. I've given you tons of practice, and some people need tons of practice, other people get it right away. But the question is, if you don't get it right away, you need extra practice. I'm giving you lots of practice, okay? And that's under modules. And I always like all my worksheets, excuse me, I always give you the answers. And I'm giving you on these worksheets, I give you all the answers, not just the even or odd ones. Okay. All right, so let's do some more practice. Okay, so we have iron 2 iodide reacts with chlorine, and normally we say chlorine gas produces iron 3 chloride and iodine gas. Okay, so first thing is this balanced? We don't know. We need to do an inventory. Okay, so we have iron, iodide, and chlorine. And how many iron on the left? We have one iron on the right, 2 iodines on the left, 2 on the right, 2 chlorines, and 3 chlorines. Okay, so chlorines are the issue. So just as a hint, whenever you see this 2 and 3 bit, think fractions. Think fractions. Not all the time, but frequently. If you're talking about even numbers and multiples, in other words, this is a 2 and that's a 4, this is a 2 and that's a 6, usually you can just multiply by something. But whenever you have this 2 and 3, think fractions. Okay, so how are we going to do this? Well, everything's balanced except for that guy. And notice it's by itself as well. So what can we multiply this 2 by to get 3? And what's nice about this is if we put a coefficient here, it doesn't affect anything else. It's just going to affect the chlorines, which is all that's unbalanced. So again, what do we multiply 2 by to get 3?
3/2.
Exactly. And we multiply 3/2, we end up with 3. So it's balanced now, but we have a fraction. We have to clear the fraction. How do we clear the fraction?
It was multiply everything by 2.
Yep, exactly. Because that's the denominator here. Okay, so I'm going to put a 2 here. 2 times 3/2 is 3. Put a 2 there because it's 1, and put a 2 there because it's 1. Now, let's do inventory again. Okay, we have 2 irons, 4 iodines, 6 chlorines, 3 times 2, 2 irons, 6 chlorines, and 4 iodides. So is it balanced? Yes. Now, what I want to talk about a little bit before we do some more examples is what does the balanced equation give us? In other words, like, so what? We balance the equation. So what? Okay. Okay, so balanced equation tells us how many molecules will react with each other. Number of molecules. Number of product molecules we'll get. The number of reactant molecules. For example, here, 2 of these will give us 2 of those. 3 of those will give us 2 of those. Now we're going to see in the next unit, we're going to be applying this ratio all the time. So we're looking at numbers and also moles as well. In other words, 2 moles of iron ferrous iodide will give us, reacts with 3 moles of chlorine gas, gives us 2 moles of ferric chloride and 2 moles of iodine gas. Okay, that's what the balanced equation gives us. And it'll give us mole ratios. Between the molecules or atoms. That's the reason we balance the equation, is we need to have those relative numbers of what reacts with what. How many of this does it take to give us so much of that? Next unit, we're going to do real life problems. I got so many grams of this. How many grams of that will I produce? You've got to know the equation. You've got to know the balanced equation to answer that question. And that's why we're spending all this time on balancing equations. Okay, so let's do some more practice here. Okay, so we have aluminum, metal, burn some oxygen and immediately creates aluminum oxide. Immediately. And this is a real important point when the world uses aluminum. Because aluminum metal immediately reacts with oxygen from the oxide, immediately. You have aluminum foil. in your kitchen. It's not aluminum foil, it's aluminum oxide foil on the outside. And the reason why it stays shiny is because that aluminum oxide film is really, really thin and the shiny metal shows through. Okay, is this reaction balanced? Well, let's see here. So we have aluminum and we have oxygen atoms. Okay, so we have one aluminum on the left, two on the right. Yep. Immediately, we already know it's unbalanced. We have two oxygens on the left, three on the right. Okay, coefficient changing time. Any suggestions where to start?
For some reason, I want to actually not start with the most complicated one this time. I want to start from left to right. So I was
Yeah.
going to try a 2 in front of the aluminum.
Okay,
I agree. I was going to do the same.
good. All right, so all that's going to change is the aluminum on the left. And hey, we have aluminum balance. Okay, what are we going to do about the oxygens? What do we have here yet again?
We need the fraction again.
It's 2-3 bit again. Yes, exactly. We have to have a fraction here. So to make the 2 the 3, we're going to go 3 over 2 again. Okay, all balanced. But we have to clear the fraction. So what are we going to do? Clear the fraction. We're going to multiply everything by
2.
exactly 4. That makes that 3. That makes that 2. Redo the inventory really quickly. So that gives us 4, 4. 3 times 2 is 6. And 3 times 2 is 6. So it's balanced. So again, we see the 2 and the 3, think fraction. And frequently it's 3 over 2. I would say 90% of the time it's always 3 over 2. Okay, so we turn on our gas stove in our house, if you have a gas stove. What comes out of the wall is mostly methane, which is natural gas. And by the way, it's odorized because methane, you cannot smell it. Okay, that was. Okay, so one carbon on the left, one on the right. Good shape. 4 hydrogens on the left, 2 on the right, 2 oxygens, and 3 oxygens. At this 3 and 2 bit again. Okay, does everyone see where I got the 3 from? 2 here, 1 here. Okay. Where do you guys want to start?
With the hydrogen on the right, because isn't that also going to affect the oxygen?
Yep, exactly. So what do you want to do with the water?
Multiply it by 2.
Okay. All right, that's going to kick our H's up to 4. And our oxygens are going to be 2 here and 2 there, so that's 4.
Now we
Mhm.
just need the 2 in front of the oxygen on the left, right?
Yeah, perfect. Now we could have also done this with a fraction. If we put 3 over 2 here, we could have done it that way too. But yeah, all done. Okay, there's numerous practice here. I just want to go over these just as a group here. Okay. Let's do this one before we do these two. There's an issue with these two I want to talk about here. Let's do this one here. All right, so we have C, H, and O's again here. Okay, 3 carbons on the left, 1 carbon on the right. 8 hydrogens on the left, 2 on the right. 2 oxygens on the left, 3 on the right. Okay. And this is what happens when you have a propane barbecue. Most of the propane is propane. It's usually not very pure, but most of it's propane. And you end up burning it. Also assumes you have a nice blue flame. If you don't have a blue flame, this reaction isn't valid. In fact, if you have not enough oxygen, in fact, let's do the problem. I'm going to show you something interesting. Okay, so obviously this is not balanced. Left does not equal right. So where do we start?
The carbon on the right.
What are you going to put? What are you going to put there?
I want to put a 3.
Yeah, okay. So that makes that a 3. Now we have 6 oxygens plus 1 is 9. Oops, excuse me. Let me back up. Oxygens are 6 and 1 is 7. Hydrogens are still 2. Okay, so our carbons are in good shape. Oxygens and hydrogens are messed up.
Then would we put a 4 on the right to bring the hydrogen up and then just have a whole bunch of oxygen?
Yeah, so that makes that 8 hydrogens. And then we have 6 oxygens and 4. 6 and 4 is 10. And we have one more step before it's balanced.
A 5 in front of the oxygen on the left.
Yep. It's balanced. Is this starting to kind of fall into place? See what I mean by guess? You go, oh, let's see, there's a 3 there. Let's put a 3 over here. And then we do inventory. We change one thing, got to do inventory. Because unless you do inventory, you never know whether it's balanced or not. Okay, so I want to look at, let's go ahead and balance this one here. Number 6 is got a little different setup. Okay, so let's look at number 5. Okay, we have P, chlorine, H, and O, all right? P, yeah. Okay, so we have 1 phosphorus on the left, 1 on the right. 5 chlorines, 1 chlorine, 2 hydrogens, 1 oxygen, 4 hydrogens, 4 oxygens. Okay, so not a good situation here. So any suggestions where to start?
I guess the chlorine
Sure.
on the right.
You can put a 6 there.
5, I think, to match it up with the other chlorine.
Yeah, I think that's a good choice too. All right, and that's going to change your hydrogens. Now we have 3 here, 5 here, that makes that an 8. Okay, so our P's and Cl's are in good shape. Hydrogens and oxygens are not.
We just need a 4 in front of the water.
Yeah, yeah. Because notice this is a 2-to-1, and water comes as 2-to-1. So yeah. Yeah. Okay. Explanation. Oh, by the way, I don't know if you've noticed, I have 2 versions of notes, lecture notes. One is an unannotated version, and the other one is an annotated version. In other words, after I make notes and all that stuff. So some of you like to start with unannotated notes and make your own notes, and other people like to have me supply you with all filled in. Okay, there are 2 ways to do this problem. I'm going to do it the way we've been doing it. I'm going to show you another way. Okay, so we have H's, P's, O, right? All right, so we have 3 on the left, 2 on the right. We have 1 and 2. And we have 4 and 1 is 5. Now over here we have 2 times 4 is 8. Oxygen. Plus 1 is 9 from the water. And calcium, we have 1 on the left, 3 on the right. Okay. Where do you want to start?
Maybe the hydrogen. This is kind of tough.
Okay, so we have 3 on the left, 2 on the right. And by the way, it's important here. There are many ways to work this problem, many places to start. You start with calcium, you start with hydrogen, you start with phosphorus, and you'll end up in the same place. Okay, so when you're working in groups and you start with an H and she starts with a Ca, theoretically, you're going to end up in the same place. Theoretically, one way is going to be more straightforward than the others. Usually, that's the way it goes. But bottom line is you can start anywhere and end up with the correct answer.
Then I think I want to start on the calcium.
Okay. All right. So which side are you going to change, left or right?
I would just left and put a 3.
Okay. All right. Got to do the inventory again. That's going to change oxygens here. So we have 4 over here plus 3. That makes that 7. Are we having fun yet?
I can see what you mean by adding more unnecessary steps. I'm trying to figure out what would be the fastest way
Doesn't have to be fast.
or least amount of steps.
Well, I mean, we have 1p, 2p's. What can we do to H3PO4 to make it 2p's?
The 2.
Here. Is that where you were envisioning it?
Is that the only place that we could put it? Can we put it anywhere else?
Well, it's either here or here. That's the only place the P appears.
On the left side.
Okay. All right, so that kicks our P's up to 2, but it's going to affect a bunch of other junk as well. Okay, so hydrogens, that gives us 6. And oxygens, we have 8, and 3 is 11.
So I guess the hydrogen on the right, changing it to 6. So multiplying it by 3, right?
That kicks that up to 6. Our oxygens are going to be 11, right? Is there 8 here? And then 3 here is 11. And I think we're done.
There's no equation that'll just have you changing it all day and it not having a true answer, is there?
Well, you may think so. For example, when you do that extra credit problem, you will think that. But it is in fact doable. Okay, so there's one thing I want you to be aware of when you're looking at these problems. And okay, the way we just did it is perfectly fine. There's another approach. Okay, another approach. Notice, okay, are there any questions about what we just did? No fractions to clear, anything like that. We all okay with this? Okay, I'm going to do this a little differently this time. Okay. I want you to notice something here. Remember from last time we had the ions? We had the polyatomic anions, phosphate, PO4 -3. We have a PO4 on the right and we have a PO4 on the left. So instead of thinking that as a separate P and a separate series of O's, let's think of that as a PO4, as a unit. If the unit appears on both sides of the equation, if it appears on both sides of the equation is the only time this is valid. If it does, then we can use a slightly different technique. Okay, so instead of tearing apart the P's and the O's, we're going to keep the PO4 as a group. So that means we have PO4s on the left and PO4s on the right. And also we have calcium, oxygen, and hydrogens. So this O and that O are not the same because the PO4Os are associated with a group. You can think of that as X. So instead of P of 4, we can write that as X. Okay, so how many X's do we have on the left?
1,
Exactly. How many on the right?
2,
And we have, like before, we have 3 H's on the right, 2 H's, excuse me, on the left, 2 H's on the right, 1 calcium, 3 calcium, 1 O, not associated with X, and 1 O on the right, not associated with X. Okay, so let's balance this equation now. What are we going to do to make the X's balance?
Multiply the left by 2.
Yeah. Okay, that kicks our X's up to 2. And kicks the H's up to 6. And hydrogens, I mean, oxygen is still going to stay 1 because the PO4 oxygens are X. They don't count as oxygens anymore. Okay, now what are we going to do?
Either the calcium or the hydrogen.
Sure.
Hydrogen, I guess, on the right. Multiplying it by 3.
And that makes that 3, right? And what are we going to do about oxygens and calcium on the left?
We can multiply them by 3.
And it's balanced. Now, did you feel this was easier to balance?
Yeah, it seemed to run smoother like that.
Yeah, the trick is recognizing the ions on the left and the right, the PO4 on the right and the PO4 on the left. Even though there is no parentheses around the PO4. But as soon as you see parentheses on the right, you go, oh, is that same grouping on the left also? Because remember with parentheses, when we have just one, see, we could rewrite this. Do a little more needed on that. See, that's the same as 1 there, if we put parentheses in. But most of the time, they leave the parentheses out because it's 1. So if you see parentheses in a big polyatomic anion like PO4, look to the other side and see if there's one there. If there is, only if there is, then you can assign it as a group. Now we got the same answer doing it the first way as the second way. Same answer. We just approached it differently. Okay, so what I want you to do is, I want to talk about the lab now. And then Wednesday, you want to talk about things like aqueous solutions and solubility and things like that. Okay. All right. So what I want you to do is you're going to need practice with these balancing equations. And because it's not intuitive, some people whip them right out. Other people go, oh my gosh. And it takes lots of practice. So I've given you lots of practice. Those are all available in modules. Okay, so I'm going to end this.